All right, here we go. Final section, 7.6, natural log and base E. So recall from earlier in the course, we've done compound interest before, and we used a pretty simple formula, and it is the amount, the final amount was the principal, which is how much you start with, and then 1 plus R was our percentage rate, like our interest rate, and then T was the time component. So let's just do an example using that so we kind of get familiar with it. And we're going to use these same numbers in 3 different examples. So we're going to reference back here to number 1 in a second. But suppose you start off with $8,000 compounded, so this 8,000 here is going to be our P. It's our starting principal. Compounded annually, which is what this equation is set up for, 1 time per year. With an interest rate of 7%, so there's my R, and I got to be careful, I want to put that as a decimal, so that's 0.07. So how much will it be worth after 30 years? So 30 is my T. So when I want to know how much will it be worth, that's the A part, that's the final amount. All right, so let's set this thing up. So we have A equals, don't want a parenthesis there, $8,000 times 1 plus 7% growth to the 30th power. And I'm going to punch that in the calculator. I'm not going to pull it up on screen just because it takes too long. So 8,000 times 1.07 raised to the 30th. So it looks like if you don't touch this money and you could earn 7% a year, which is what they say the stock market is roughly 7 or 8% a year. You would have, if you didn't touch it, $60,898.04. So that's kind of a lesson in why you want to invest early as you can, let time compound it, and it's a pretty substantial amount of growth from 8,000 to 60,000. All right, in the real world though, investments or debt may be compounded quarterly. All right, quarterly means 4 times per year. Monthly, 12 times per year, or even daily. Like a lot of times when you look at your credit cards, the interest against you, your debt is compounded daily, 365 times per year. So like let's say that it was an investing problem and they were compounding your interest daily. You don't get 7% a day. You'd be a billionaire pretty quick. But you take that 7% and you divide it out over 365. So you're getting a very tiny percentage each day, but every day you're taking a percentage of a little bit bigger of amount. So it snowballs daily as opposed to waiting till the end of the year to do it once for 7%. So in this next equation, we can tweak a few things, and there's some ends here. So it's kind of a similar equation, but you notice the ends, and what the n would represent is the number of times that we compound it per year. All right, so you'll notice there's a little n where we're dividing the interest rate, and then there's an n by how many times it's being compounded if t is in years. So this is called the compound interest formula. So we're going to use the same info as above, but we're going to see what if they compound it monthly. So what if, think about this. If you get 7% for every year, well, if we compound it monthly, if we divide that 7% up, divided by 12, all right, let's just pop that in our calculator real quick. So 7 divided by 12, roughly, we are getting 0.583 repeating percent per month. So it's still 7% a year, but it's 0.583% every month, but every month it's growing to be a little bigger number. So I keep taking the 0.58% of a bigger and bigger and bigger number, which is better for me if I'm investing. It's worse for me if I owe somebody. But that kind of gives you your new little monthly percentage rate. So let's kind of do this example with the same information. So what is our final amount going to be? If we start with 8 G's, we do the 1 plus 0.07, and then here is where the monthly comes in. The word monthly, I'm going to put a 12 down here. And then up here on my exponent, it's going to happen 12 times a year. So I have to do 12 times t, but we said that t was 30 years. So that's actually going to be a 360 up there. So you got to be careful with how you enter this in the calculator. I'll go over this in class, but just for time's sake, I'm going to just do it on the handheld here. So 1 plus, I'm going to do a parenthesis, 0.07 divided by 12, parenthesis, I got to do 2 parentheses there. So I kind of, when I did it in my calculator, I put parentheses around that. And then I'm going to raise that to the 360th power. And I get a final number of $64,931.98. All right? So, and then the question says, how much more will you have if we did it monthly instead of yearly? Well, the first example up above was, I still have it on my calculator here, 60,898.04. So when I subtract those two numbers, minus 60,898.04, it looks like I get an extra $4,033.94 by compounding monthly instead of just once a year. So it definitely is in your best interest when you are investing. The more often it's compounded, the more money you're going to make. It's kind of the big takeaway. The reverse is true when you owe money and there is a debt involved. All right, so we've used compound interest. Let's go down. So as n gets bigger and bigger, so credit cards would be compounded daily. They use the number 365 for n. But as you keep making that n get larger and larger, 1,000, 10,000, million, interest or decay is called compounded continuously. Because when you think about, like, let's say you have bacteria in a petri dish, and it's doubling every, 10 days, let's say. Well, it doesn't wait 10 days and then just magically double. Like, it's continuously working towards that double. So this new formula that I'm going to give you here is very important when it comes into real life, and especially with like radioactive decay. Not as much investing, a little bit, but definitely more with science and decay of elements and items and different substances. So it says as n gets extremely large, compounded continuously. If you graph this function right here, and you start looking at it, kind of bring this up a little bit. If you graph this function up here at the top, and you just leave the n in there, and you keep going to the right, bigger and bigger and bigger and bigger n's, what you notice is this graph, it comes up, and then it kind of plateaus, and there's actually an asymptote right there. Remember, an asymptote is a line, it's kind of like a force field that never gets crossed. Well, there's an asymptote there, and it came out to be a really important number. And the number is 2.71, and as technology gets better and better and better, we can get more and more and more digits. But it's a number that goes forever. And this number is called, it looks like Euler's number, but I've been told, and I think I looked it up, and it's pronounced Euler. So Euler's number, and it's represented by the letter E. So you see this little kind of italicized E. It's kind of similar to pi. We know that pi is 3.1415269, blah, 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 blah. It goes forever. Well, this number comes up a lot in nature. So they decided to give it a letter and give it a name. And so E equals this number here. And it's because of continuously compounding where it approaches, like as you just go further and further out. The big thing we need to understand is exponential functions with E as the base, they have the same exact properties as the other logs that we've studied. All right. So first we're going to do a little graph here. And I think I'm going to kind of cheat, and I'm going to do this one on Desmos. So I want you to graph e to the x plus 2. And think about in your mind, this is really just y equals 2.71 blah, 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 to the x power. You know, so it's something just like, you know, y equals 2 to the x, but it's a little bit bigger. Plus 2. Let's just kind of see what that looks like in Desmos, just so you can verify it is exponential. So I'll pull Desmos up here. And y equals e, and it knows what e is. See, it automatically popped up over here. E raised to the x power. And got an arrow over. So you can see that's exponential. And it crosses at 1 because anything to the 0 power is 1. So you'll notice that point's on there. And then if I do like a plus 2, it's just going to shift it up 2 units. You know, if I compare it to the parent function, y equals e to the x, you'll notice it's the same curve, just shifted up 2. I could minus there and it would go down 2. So just want you to kind of realize that it is an exponential curve. It just has this special base that we started talking about. All right, so let's go back to our notes. You could graph that if you wanted to on the graph. It's not really that big a deal. But here's where we start getting into the nitty-gritty. So, and where we're going to actually apply some of this stuff. So logarithms with base e are called natural logs. All right, so whenever you hear the word natural log, that means that it's a base e. All right, so log base e is a natural log. And they're usually abbreviated. I'll be writing it as like ln. A lot of times in books it won't be a cursive L, but I don't want it to look like 1n. So I'm kind of using that script. So it's ln. Or on your calculator, the key on your calculator is going to be, you know, big Ln. And maybe I'll pull up the calculator real quick just so you can kind of see where it's at on your TI. So let's kind of pull him. I'll just leave him right here. Let's quit out of that. Clear this out. So if you notice, right beside the 7 is the log key. And then right beside the 4 is the ln, the natural log key. All right. Now you'd never do log, natural log altogether, but I just wanted to show those. You also can look on there and you can see that the number e is right above the natural log key. So if I hit second natural log, that's how I get the e in there. So all those log keys and e's are kind of right next to each other. They're all right over there in that little area beside the 7 and the 4. Now natural logs, they have the same exact properties as regular logs with base 10 or other bases. So, you know, the quotient property, product property, power property, change of base, all that good stuff still works with these guys. And then also what you need to know is the natural log of x and e to the x, these are inverses of each other. So meaning that, remember, inverses on a graph, if you were to graph them, and we kind of looked at e to the x, kind of did something like this, well, our natural log of x is going to come up, and it is going to look something like that. Because remember, it's going to be symmetrical along that line, y equals x. So, you know, this would be e to the x, and this would be the natural log of x. So the big thing is they undo each other. E to the x and natural log of x undo each other. Kind of like if I said, hey, you know, 3 to the x power, and we were to graph that, and then we do log base 3 of the x power, those two are inverses of each other. All right, so it's very similar to the same thing, but e and natural log kind of undo each other. So let's do a couple just basic problems. There's not going to be near as many solving problems in this section as there was in the last one. There's going to be a couple more story problems, but they're a little bit longer and tougher. So it says, simplify the expression below with e or natural log in them. So I have this expression that says natural log of e to the negative 2t. Well, remember that natural log can just be rewritten. Like if I wanted to do this the long way, natural log is basically just saying, hey, log base e, all right, of e to the negative 2t. Well, we kind of had a property earlier, an inverse property that said whenever you have log base something, and then you have the something right next to it, this almost kind of cancels each other out. And you just end up with an answer of negative 2t. All right? And if I really wanted to kind of drag it on out and show you the long way, I could say, well, natural log is log base e of e to the negative 2t. And then I could be like, hey, write this in exponential format. And you're like, okay, I could write this in exponential format. That means that e to the question mark equals e to the negative t. And you're like, oh, well, question mark is obviously just negative 2t. But you can save a lot of work by just seeing that natural log and e cancel each other out. All right? They just kind of squash each other. And the same is true over here in the next example. When you have e raised to the natural log, it's also going to be the exact same thing. The e and the natural log are going to wipe each other out. And I'm just going to end up with t minus 1. And similarly over here in number 6, we have e to the 5 natural log of x. Well, remember our little exponent rule. Whenever you have a natural log, you can kind of move that up to the top. So e to the natural log of x to the 5th, well, the e and the natural log wipe each other out, just like they did over here, just like they did over here. Natural log of e, or e to the natural log. And I just end up with x to the 5th. All right? And I'm not super concerned right now, like how much we grasp that. We'll get some practice just recognizing that you can cancel. Anytime you have natural log e, they can wipe each other out. Or anytime you have e to the natural log, both of those are inverses, and they can kind of squash each other. And you're just left with the other stuff. But the interesting part is when we get into some story problems. So this first one's not too bad. The second one is a bit more involved. So, when we get to number 8, you're going to have to battle with me because it's kind of long. But number 7 says the use of E simplifies the continuous compound interest formula to, that big old crazy formula we had earlier that was A equals the principal 1 plus R over N to the NT. That's good if you're compounding monthly, daily, quarterly. But if you're going to do it over and over and over, and N just approaches infinity, like N just gets bigger and bigger and bigger, all of that simplifies down to just A equals P e to the RT. I kind of always remember this is like the shampoo equation, because there was a shampoo called Pert back in the day. Don't know if it's still around. But that's how I remember this one. So let's see, I told you before that the more often you compound, the more money you're going to make. Well, let's do our beginning example. $8,000 invested at, this is going to be E to the RT, which is 0.07 times 30 years. All right. And let's go ahead and just punt this in our calculator just so we can kind of see what it looks like. So I can show you doing the E key. So turn this thing on. So we have $8,000 times E, so I'm going to go second natural log, to the RT. Well, R was 0.07 times T. I don't know if I have to multiply there or not. I'm just going to put my T in and not multiply it. And let's just see what that comes out to be. 65,329. All right. So $65,329.36. So you can see from compounded yearly was somewhere around 60 grand. Compounded quarterly, or monthly, was 64 grand. You're not going to get any better than that. That's compounding every second, every millisecond, just over and over and over. But we're splitting up that 0.07 infinitely and compounding. And that's where this letter E comes into play when it's continuous. All right? So there's an investment example. Now this will make Rod happy. This is a decay example. So since the natural decay of a substance happens continuously, meaning that if I said, hey, you know, you have a certain amount of some sort of substance, maybe you take an aspirin, and over time there's going to be less and less and less aspirin in your bloodstream. Well, it doesn't just, it's not in there like 100% and then all of a sudden it just disappears and it's gone. Or the half-life doesn't just magically occur, you know, at an hour, all of a sudden half of it's gone. It's like you're slowly losing it, all right? So since that's continuous, there's this equation that we can use, and this is kind of a science equation that basically, I'll tell you what these means. This is the amount left, this side of the equation. That's how much is left, or the final amount, I guess you could say. This n naught, n sub 0, this is the initial amount, kind of like your principal. The n0, n sub 0, that's really not a number 0, it's just a notation. The initial amount that you start with. And then E, of course, we know what E is. E is 2.71, blah, 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 blah. T is time. All right, so the T here is time, whether it be minutes, days, hours, years. You know, carbon has a half-life of like 5,730 years. So it takes a long time to lose half of your carbon, where other things decay much quicker. And then you have this tricky part. This, I wish I had another color here that I hadn't used. But you have this negative K, and this is called the decay constant. And this is the most important piece of this formula. That's the hard part of this formula. All right? So usually we want to know how much is left, or we might want to know how much time. We usually know how much we're starting with, not always, but those are all different variables that we may not know. So let's try to put this into an example, and I'm going to warn you, this example is not the easiest example, so stay with me. Try to battle. That's why you guys are in honors. So here we go. It says determine how long. So we are solving for T. Will, apparently I couldn't spell will there, will it take for 650 milligrams of a sample of chromium-51, which has a half-life of 28 days. This is going to be important. Half-life of 28 days. And we want to know, when is it going to reduce down to 200 milligrams? So this is going to be my final amount. This is my n, all right? My n sub 0, my starting amount, is the 650. We're trying to find T. We know what E is. But you're going to notice, like, we have a bit of a problem because we don't know T. We don't know how long. Because if it said how long is it going to be at 325, we would know that answer. That's 25 days. But we don't know the constant. We don't know K. So my whole problem here, and what it's usually the problem is, we got to figure out what the decay constant is. All right. So check this out. So let's just start off with what we know. We know that we need to get, well, maybe let's start off with this. I know for sure that if we start with 650 milligrams, all right, to the E power, I don't know the negative K, but I do know when it's going to be cut in half. I do know it's going to be 325 when T is 28. All right, because that's the half-life. Now, I don't really need to do this math. You could put your starting amount and then calculate what half of it is, but I'm getting ready to divide both sides by that 650. So in general, if you're dealing with half-life, you could always just start off doing like 0.5 to 1, because you know it's always that's going to be half of your starting amount. So if you want to, you could just kind of zoom right into this step right here and then kind of start rocking and rolling. So the only thing we don't know there is K. So this is going to be like a two-step problem. So what's going to happen is we're going to do step 1 and we're going to find K. And then step 2, we're going to use k to find t. All right? So step 1 is going to be here on the left. So I have this equation. It's got an exponent in it that I need to solve for, so I know I'm going to be able to use log somewhere. Well, the first thing I want to do is I want to get rid of that 1 right there. So I'm just going to divide both sides by 1, which really doesn't do anything. So it's kind of just going to wipe out this 1, because 1 times e is just going to be 1. So don't worry about that piece. Well, now I'm trying to solve this, and I'm like, well, I need to get rid of that e. So to get rid of the e, if I take the natural log of both sides, maybe I could put this in black just to show you. The blue is what I'm doing new. If I take the natural log of both sides, and I'm just going to call this negative 28k. I'm going to multiply those together. Well, taking the natural log of both sides, I can see over here on the left, I just end up with natural log of 0.5, which let me put this into my calculator. ln 0.5. I get a decimal. Now, I know like Miss Mahaney probably in pre-calc, she's probably going to have you keep this natural log of 5 all the way to the end. I think for us it's going to be easier to maybe just keep like 3 or 4 decimals, and it's going to be a little bit easier to work with. So let's just get rid of natural log of 0.5 and let's put its value in here. Now here's where we get to use that power up above. The natural log of e cancels out, and it's just going to be because they're inverses. It's just going to be equal to negative 28k. All right? Well, now I can solve for k. I can divide this side by negative 28. I can divide this side by negative 28. And I get k equals, and my number's right in there, that 0.69 number, so I'm just going to use answer divided by negative 28. And I get 0.024755, blah, 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 blah. All right? And that's far enough. We're gonna be close enough by rounding, somewhere far out, not to the nearest tenth or anything. So I've achieved step 1. Step 1, check. I found k. Well, now we're going to go in and we're actually going to try to solve the problem. So now for step 2, let's use the numbers they give us. We want to know, when the heck are we going to get to 200? We started with 650. We want to end with 200. We know the equation has an e in it. We know it has a negative k, but now I know what k is. Now I'm like, oh, I know what k is. It's, 0.024, I don't know. I might as well just put them all there. Let's be really accurate. Blah, 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 blah. But we don't know t. That was our ultimate goal in the very beginning, was how long. All right, so I don't know t. Well, I'm going to do the same exact process again. I have an equation with an exponent that I need to solve for. So I'm going to go down the same road. So on this case, I'm going to divide both sides by 650, because I want to get that e by itself, that e term by itself. So divide by 650. And over here, I'm going to get e to the negative 0.024755 t. And on the left-hand side, some classes, they probably just have you leave that as a fraction or simplify the fraction. I'm going to get a decimal. Let's just rid ourselves of fractions since we're first learning this. And I end up getting, when I did that division, I get 0.307, let's just call it 69. We'll stop there. All right, well, just like I did on the left-hand side, once I get it down to an exponential equation, I'm going to take the natural log of both sides because I want to get rid of that e. So I'm going to natural log this side. I'm going to natural log this side. Boom, you gone. And now I get negative 0.024755 t. And on the other side, I got to use my calculator. I'm going to just hit the ln button. ln 0.30769. Thank you, whoever programmed this calculator to do all this for me. And that works out to be negative 1.17866, blah, 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 blah. Well, we got one step left, man. To get t by itself, another division move. Divide by that thing. on both sides. And I got to punch it in. Luckily this top number is still in my calculator, so I'm just going to hit divided by, and it puts answer in there for me. Negative 0.024755 equals, beautiful. I'm getting 47.6. And what were we talking about? We were talking about days, all right? We had half of it in 28 days. So it looks like we're going to get down to the 200, because that's more than half. You know, if you start at 650 and you go down to 200, it's 47.6 days is going to be how long it takes to get to 200. Now, you could kind of ballpark this. If I wanted to just kind of do some quick and dirty math, I could be like, well, you know, if I start at 650, whoop, you know, and just to see if I'm on the right track. If I start at 650, well, 28, this is day 0. All right. On day 28, the half-life, that would put me down at 325. Well, if I go another 28 days and I'm at 56 days, half of 325, that's what, 162.5? Well, that's too far. I've went past 200. So I know that 200 occurs somewhere in here, and it's going to be closer to the 56 than it is the 28. So I think that 47.6 looks like it could work. So you should always be able to kind of ballpark and just see if you are on the right track. I know that was a tough example. This isn't easy. We will get more practice. We're going to have a couple days to review. So good luck with the practice. See you.